All right. Good morning, everyone. And we're going to carry on our discussion today about circulation system and about gas exchange. Only very briefly talk about gas exchange. We'll spend most of our time actually talking about circulation. And our discussion today, I want to emphasize, is about the blood circulatory system, because we're going to hear about another circulatory system, which is the lymphatic system, which we'll hear about when we talk about the immune system. Okay, so this is where we finished off last time. And just to orient ourselves, talking about this incredible organ, the heart, which is characteristic of all of the vertebrates, and in the mammals and the birds has a particular structure, which is that it drives two completely separate circulatory systems. So we're going to explore today exactly how that is done. So to orient ourselves, first of all, there are 4 chambers to the heart. There are 2 atria, which are here, and the atria are muscular, but they are thin-walled. They are muscular, they contract to drive blood, but they've only got to drive blood a short distance and through giant valves. So they don't need much to exert much pressure to do so. And they drive blood into the ventricles. But the ventricles have to drive blood much further under much greater pressure. So the ventricles are thick-walled and heavily muscled. So this here is the right atrium. It leads into the right ventricle. And it does so through a valve here, a very big valve, called a tricuspid valve, and tricuspid because it has 3 flaps to it. You'll see it's also got this name, the Atrioventricular Valve. That means simply means it lies between the atrium and the ventricle. And this valve here prevents backflow of blood into the atrium. We'll hear a bit more about it in a while. From the ventricle, from this right ventricle, blood is driven to the lungs to be oxygenated through this vessel here, and that is the pulmonary artery. Artery because it's carrying blood away from the heart to the lungs, even though it's carrying deoxygenated blood. Again, there is a set of valves to ensure the blood flow is one way. It leaves the ventricle and travels this way through these valves here, which are the Semilunar Valves. So that this whole circulation system here is getting deoxygenated blood and supplying it to the lungs. The blood returning from the lungs, which is oxygenated, returns from the pulmonary veins. Here they are here, there are 2 here. There are another 2 here that come around the back here, and they feed into the left atrium. Just like the right atrium, it's a thin-walled muscular chamber that drives blood. When it contracts, it drives blood into this ventricle here, which is the left ventricle. The left ventricle is the biggest chamber of all, and it's got the thickest walls and the most muscle, because the left ventricle is receiving this oxygenated blood and now has to distribute it through the whole body. So it needs to generate a lot of pressure. Again, there is an atrioventricular valve here, and this one only has 2 flaps, so it's called a bicuspid valve, and it has another name that you may have heard of. It's called the mitral valve. And so this is the mitral valve here, and that is important. The mitral valve is important because it is one of the strongest valves. It has to resist a tremendous amount of pressure when this ventricle contracts. All of this blood needs to be driven out to the rest of the body, and it goes out here through the aorta there. And that's the aorta supplies all of the rest of the body with blood, as we'll see in a second. So what we see, right atrium, right ventricle deal with deoxygenated blood. Left atrium, left ventricle, they deal with the oxygenated blood. The 2 circuits are kept completely separate from one another. Okay, so that we're going to follow the path of the blood through the heart and then through the circulatory system, just to see how it goes. Here's the right ventricle. Here, deoxygenated blood needs now to dump its carbon dioxide and pick up oxygen. And so it is driven by the right ventricle out through the pulmonary arteries to the lungs. Here. In the lungs, it goes through a very elaborate set of very, very fine vessels called the capillaries, the pulmonary capillary bed. It dumps all its carbon dioxide and picks up oxygen. And now is returned to the heart. And it's returned because these vessels are flowing towards the heart. They are veins. These are the pulmonary veins, the left and the right pulmonary vein. And here, just give me 1 second, please. I just need to do something here. Okay. Are you all with me? Sorry, I just needed to do that because otherwise it goes bong, bong, bong through my whole lecture.
Yeah, okay.
Okay, fine. All right. So we've got we have our blood's been oxygenated. It's got to be returned to the heart. It's returned through the pulmonary veins. Here, one instance where veins are carrying oxygenated blood. Here's the left atrium here, the left ventricle. That's the Atrioventricular Valve. And this is the most powerful chamber of all. When it contracts, it generates a tremendous amount of pressure on the blood, and it's forced out through this huge vessel here called the aorta. And the aorta divides. It divides into one branch, which supplies the head and the trunk with oxygen there, and it is returned to the right atrium through this vessel here, which is called the superior vena cava, to the right atrium. The other branches of the other major branch of the aorta carries blood to the rest of the body, all the way along here. They haven't drawn it, it's just simplified. All the way along here, there are branches which go off to the different organs. It's just shown as this capillary bed, but realize that it becomes very, very complex because it's supplying all of the organs of the body. It's dumping its oxygen, providing oxygen to all the tissues, providing nutrient to all of the tissues, and at the same time picking up carbon dioxide. The deoxygenated blood is returned to the heart by the inferior vena cava. That's this vessel here. And it also dumps into the right atrium there. So through the right ventricle, lungs, left atrium, left ventricle, aorta, and off to the body and back again, and so we go. And what we see is that there is this complete, there are two circuits. There's this circuit through the lungs, and then there's this circuit through the body, and the two are kept completely separate. And the deoxygenated blood is completely separate from the oxygenated blood. We never get any mixing of the blood. Unlike, if you just think back, although we didn't do it in great detail, if you think back to that amphibian system, they did not have this complete separation. They have a certain amount of mixing of the blood. Okay, so are we all right with that so far? All right, so now let's just have a look at how, obviously, this pumping action is very important and it's got to be very carefully coordinated. We've got to pump blood from the right atrium to the right ventricle. We've got to pump blood from the left atrium to the left ventricle, and then to lungs and body and everything else. Obviously, the beating of the heart has to be carefully synchronized in order to do this properly. And in fact, if this beating of the heart goes wrong, which it can sometimes do, it is a critically dangerous situation, because then the body is not being supplied with oxygen properly. The contraction of any chamber is called systole. So S-Y-S-T-O-L-E. So contraction is systole. Relaxation is diastole. And so when a chamber is in relaxed state, it is in diastole. And that's where we're going to start off with this heartbeat. We're going to start with both, all of the 4 chambers are relaxed, and they are in diastole. They are in atrial and ventricular diastole. The first part of the heartbeat is the contraction of the atria here. So the atria now have contracted. They have gone into systole. And because their volume has decreased so drastically, they have to pump all the blood into the ventricles. So the ventricles fill, but they fill passively under the pressure of the atria. Now the atria relax and the ventricles contract. So we have now atrial diastole and ventricular systole. And the ventricular systole squeezes the blood out to the lungs and out to the body. And then we return to a recovery, a relaxation, and then we have our next heartbeat. Contraction of the atria, the relaxation, contraction of the ventricles, and so on. And now you see the importance of these huge valves, because when these ventricles contract, for instance, they contract and produce a tremendous amount of pressure. And if it were it not for those valves, the blood would simply be forced back into the atria. But it's not, because there are these huge valves, tricuspid valve there, and this mitral bicuspid valve here, and those close when under the force of that back pressure, they close, and they prevent the blood from going into the atria, and instead force it out through the great vessels here. Likewise, here there is this here is called a semilunar valve, and there is another here, another semilunar valve there. When these ventricles go into diastole and relax, there's an impulse for the blood to flow back into, but it can't, because these valves here now close and prevent the blood from flowing back. They slam closed, in actual fact. When these valves close, for instance, in systole, in ventricular systole, when these atrial valves slam close, it makes a sound. It goes lub. And when those ventricles relax and these slam close, these semilunars here slam close, they go dub. So that gives you the heartbeat. It's lub, dub, lub, dub, lub, dub. That's our heartbeat. And it's clinically very useful because of that sound. When the doctor listens to your chest, she's listening for a clear lub, dub sound, which indicates that the valves are slamming closed properly. If there's any error, which can happen, if the one part of the valve is not closing quite on time or something like that, it makes an additional sound, often a whooshing kind of sound, and that is called a heart murmur. Many people have heart murmurs, by the way. If a doctor says to you that you've got a heart murmur, don't panic. Many people have slight murmurs. They're called benign murmurs. It just means that the valves don't close absolutely synchronously. Is there anything else I need to tell you? We run through it again. Atria close, then the ventricles fill, then atria relax, ventricles contract. And that is the circuit of the heartbeat. The heart rate, the number of times that it contracts per minute, is the heart rate. And that you can measure by going down to a pulse point. a place where an artery, for example, runs over a bone or runs close to the surface of the skin. You can put your fingers on it and you can actually feel the heartbeat because of the tremendous pressure being caused by the contraction of the ventricles. That pressure is communicated throughout the arterial system. It is so strong. The amount of blood that the heart pumps through in a single contraction is called the stroke volume. And the cardiac output is the volume of blood times the heartbeat. That's your heart. That is the cardiac output. It's the volume of blood that your heart is pumping per minute. And all of these, the heart rate, the stroke volume, and of course, then thus the cardiac output, is carefully monitored by your body itself. You have monitoring systems to maintain the correct amount of blood. This cardiac output will be increased if you are exercising, for example. It is decreased if you're at rest. And that is under control of the autonomic nervous system, which is monitoring. There are sensors which are monitoring blood pressure, et cetera, and these can be modulated to provide the optimum cardiac output for whatever the body requires. Okay, so please make sure that you understand all of these. I'll just point out a little bit more about the anatomy of the valves for you, because these valves are so important in the functioning of the heart. So again, these are here. Let's just have a look at these. These are the atrioventricular valves because they lie between the atrium and the ventricles here. And they consist of these flaps of tissue there, but they are tied to the wall of the heart by very strong tendons that run down. You can see them running down there, and they're attached to the muscle here. Same on this side here. They are these valves especially are very, very intricate and extremely strong because they have to resist such a tremendous amount of pressure from the contraction of the ventricles. These here are the semilunar valves, and if you can envision, these are almost like balloons, like three balloons lying next to one another, and if any back pressure of blood here fills those like sails and pushes them against one another to prevent blood from flowing back. Okay, so this beating of the heart is obviously very, very important, and it's very important that it be carefully controlled. There's an intricate system for ensuring a correct heartbeat. There's a strange feature of cardiac muscle, and that is if you can culture cardiac muscle, for example, you can culture it in a petri dish if you wanted to. If you do so, you see something very strange about cardiac muscle, and that is that the cells generate their own contraction. So it's unlike other muscle cells which only contract when they have a nerve impulse. The cardiac muscles generate their own movement and contract. And if, for instance, if you have a culture of cardiac cells, they communicate with one another within a certain distance and all contract together. But that contraction, if you were to expand it out to the whole heart, it would just be chaotic. Different groups of cells will be contracting at different times. And instead, this chaotic contraction of the cells is coordinated, and it's coordinated by nerve impulses which are generated, which run through the whole heart periodically to get them all to contract at the same time and to coordinate this heartbeat. And this control is through a set of concentrated nerves which generate their own impulse. And these are called the pacemakers. So there's kind of autonomous little clusters of nerves which generate nerve impulses periodically. And they are named for where they are. So for example, this here is the sinoatrial node there, because it's on the atrium. This is the atrioventricular node. And the sinoatrial node is principally responsible for coordinating the contraction of the atria. The atrioventricular node is primarily responsible for the contraction of the ventricles. It's a little bit more complicated than that, but anyway, we'll keep it at that simple. So let's have a look. Remember, it's generating electrical impulses, what we can measure as electrical impulses. Here they are. So this is a sinoatrial node, and it's generating an impulse, which is going to cause systole in the atria. And you can see the yellow color there. It spreads through nerve branches, which run throughout the muscle. And that impulse sent out by the sinoatrial node causes all of the cardiac muscle cells to contract at the same time. Instead of chaotic, it all contracts at the same time. Once that is done, it actually communicates with this node here. But once this contraction of the atria is complete, this node here generates a nerve impulse, which runs down and relatively slowly spreads through all of the walls of the ventricles. And that causes a coordinated contraction of the ventricle muscles from the bottom to the top, which squeezes the blood up through the vessels and into the circulation. So the fibers, by the way, the nerve fibers, they are called the Purkinje Fibers. Those are the fibers that feed out into the muscles of the ventricles. Those of you who are going to be doing your MCATs, you might want to remember some of these names. Because it's electrical, we can actually follow the course of the heartbeat by measuring electrical impulses generated by the pacemakers. In fact, those electrical impulses don't just stay on the heart. They are spread throughout the body. Doesn't have any effect on the rest of the body, but they can be measured at other parts of the body. And if you've ever had an ECG, an EKG, EKG, by the way, is the same thing. It's just a German acronym. But if you've ever had an EKG, you know they put sensors all over your body, and this is exactly what they're measuring. They're measuring what is happening at those pacemakers. And this is how, when this is probably familiar to you, the Ekg Ecg Trace, and this is what it looks like. There's a little bump here, a little change in voltage here, which is because of the sinoatrial node generating an impulse, and that causes atrial systole. Then there is a firing here, which you see here, of the atrioventricular node, and that rapidly spreads through the whole heart. And then causes this ventricular systole here, which is here, that peak there. So we got atrial contraction spreading through, then the impulse generated by the AV node spreading through the heart, and then a contraction of the ventricles there. And this bump here is actually the heart resetting itself. In that phase when the heart relaxes completely, the nodes, the pacemaker nodes reset themselves and get ready for the next one, and that's recorded as this little change in voltage here. So here it is here. This is atrial The depolarization, you won't mean anything to you at the moment because we haven't done nerves yet, but the depolarization means that it's going to be generating an impulse which will cause contraction. So depolarization, there it is there. Here's the ventricular depolarization here. And here is where the heart resets itself. It repolarizes, and that's the repolarization there. Don't worry about these, unless you're doing MCATs. If you're doing MCATs, you might want to make a note of these different segments, P, Q, QT, and ST. They may ask you in MCATs. Okay, so the heart in a way is almost independent. Its beating is almost independent. And in fact, if a heart is taken out of the body, as it is when we do heart transplants, for example, the heart will continue to contract in a perfectly coordinated fashion, even when it's out of the body for a while, because the pacemakers are independent. They generate those impulses all on their own. But the pacemakers can be controlled. They can be made to speed up, and they can be made to slow down. And they do so in response to impulse from the autonomic nervous system. Remember that what is happening is the body is monitoring its demand for oxygenated blood the whole time. And if the demand rises for any reason, then an impulse is sent to the pacemakers to speed up heartbeat and hence speed up cardiac output. In addition, we'll hear that the diameter of vessels can be changed. So, and not only that, the strength of the heartbeat can be changed. The body has very fine control over cardiac output because it's one of the most critical things to ensure that the body has correct supply of oxygen the whole time, no matter what the body is doing, no matter whether it's running from a lion or if it's lying down reading a book. Okay, we've got to have the correct cardiac output to provide the optimum conditions for the body. The sympathetic nervous system is what speeds up the pacemaker, sorry. And that should make sense to you. I think I've referred before to the action of the sympathetic nervous system. For example, this is the sympathetic nervous system when you get a fright. It is the sympathetic nervous system that activates you, that makes your heart beat faster, pushes your blood pressure up, pushes the blood pressure up to correct the correct areas of your body, to your brain, for example. The parasympathetic nervous system is that part of the nervous system which slows down the pacemaker. It's the calming part of the autonomic nervous system, reduces heartbeat, reduces blood pressure, because in those times when there is no demand for a high blood pressure. Those pacemakers are also controlled by, there are other hormonal influences on them as well, which we won't discuss, some of them quite extraordinary. There are hormones from the kidney, for example, which can have an effect on the pacemaker. Okay, let's have a look here at sorry, I just need to get rid of your pictures. I'm afraid are sitting right over my screen. There we are. Okay, I just want to very briefly show you some of the features of the different blood vessels, because this becomes really important in our discussion, for instance, about blood pressure and this sort of thing. So obviously we already heard, there are two main species of blood vessel in the body, and these are the arteries and the veins. The arteries, those great vessels leading away from the heart and carrying blood from the heart to some destination in the body. The veins are those vessels which feed into the heart. And the arteries, we need to remember, are under high pressure. And that is because of this tremendous amount of pressure generated by the left ventricle especially. The veins, we're going to find out, are not under that kind of pressure. And in fact, the blood pressure in veins is extremely low. The blood pressure in the arterial system is very high, comparatively. So these are veins here, and these are the arteries here, and you immediately notice that the arteries are thick-walled, and the veins are not. They both have basically the same anatomical structure. That is, they have basically 3 layers. This is called the Tunica Externa, and it's a covering around the vessel, which has a lot of connective tissue in it. It gives structure and strength to the vessel. On the inside here, there is, it's called the tunica media there, and it's muscle. It's a muscle layer. And it has a special function that I'll discuss in a second. Then on the inside here is a layer called the Tunica Intima, the innermost layer. And at the moment, this is a layer we should be very, very interested in, because it's made of cells called the endothelial cells, and it's often called the endothelium. And it's the layer on the inside of all of our vessels, both veins and arteries. And it has a special structure. It is extreme, as far as the blood is concerned, is extremely smooth. And that is so that blood does not stick to it. The blood skims over the top of it as it's moving. We'll find out in a moment why that is so important. As soon as we stop blood, it starts to clot. The reason I say that this is something that we should be very interested in at the moment is because it appears that COVID, the SARS-CoV-2, which is called COVID-19, actually attacks these cells. And this explains many of the effects of the disease COVID-19, because many of the effects of COVID are due to inflammatory processes. And depending on which blood vessels are attacked, where, we get different symptoms, different disease profiles for people. So this is really important to us at the moment. These endothelial cells, in this case, appear to be vulnerable to that virus. So in any case, the veins are thin-walled. These layers are all thin. The vessels cannot actually withstand much pressure at all. In the case of the arteries, on the other hand, they have to withstand a lot of pressure. The vessels which lie close to the heart, in fact, have an additional structure to them, which I'll show you now. But here's the same layers, Tunica Externa there, but in the case of arteries, it's thick and tough. Here's the Tunica media here, and in the case of arteries, again, it's thick. And here's the endothelial cells, they're not that much different to the veins, but in close to the heart, these vessels have an additional feature, and that is they have a tough elastic layer. And the best way to think about it is like a hose pipe. If you look at a hose pipe, you know, they have all the reinforcing, they have plastic, whatever, but inside the plastic, they have reinforcing so that the hose pipe resists the pressure. It resists the impulse to expand under pressure. Instead, it stays the same diameter, exactly the same here. It's a mechanical feature to ensure that the vessel does not do this every time the heart beats and dissipate that pressure. You want all that pressure to be transmitted throughout the body. As the artery, as we get somewhat smaller, as the artery, what goes away from the heart, this layer disappears. It's not needed anymore. But we still have a tough outer layer, a thick muscular layer, and then the endothelium. But then, as these vessels go further and further away, as they feed into the organs, for instance, and into the muscles and everything, they begin to divide. And they divide and they divide into smaller and smaller and smaller little tubes. And these are called the arterioles. And here's an arteriole here, and you'll see that it's lost its outer layers. There, it does no tunica externa anymore. It's just got the muscles around it and the endothelium. And then ultimately, these arterioles get even smaller and they form capillaries. And the capillaries lose even the muscles around the outside, and it's just the endothelial cells. And these capillaries, these arterial capillaries, join up seamlessly with venous capillaries here. The veins, we see the same kind of progress of the anatomy as we divide and divide and divide and divide the veins as they get further and further from the heart. We see that they get smaller, and then ultimately they form little thin veins here, and ultimately these venous capillaries, which join up with the arterial capillaries here. So the whole structure of the artery is so to maintain that pressure from the heartbeat and get the blood flowing as far away from the heart as possible efficiently. So when we measure the pressure in the arteries, if you put your fingers on your pulse here next to your thumb, you'll feel gadum, gadum, gadum. Obviously, you have an increase, decrease, increase, decrease, increase, decrease in the pressure. And the increase in pressure is due to the systolic beat of the ventricles. The ventricles contract, pressure rises throughout the arterial system. And we can feel that as our pulse. But we can also measure it. And we measure that as the systolic pressure. When you have your blood pressure taken, they should always take your blood pressure from your arm on a level with your heart, so that you're measuring more or less the pressure inside the heart. And the beat of the heart produces a pressure, which is the systolic pressure. That's the high number of the blood pressure. The diastolic pressure is the resting pressure. In between a heartbeat, there is still pressure inside the artery. And that is the diastolic pressure. And that's the lower number of your heart when they measure your blood pressure. For most young people, a normal blood pressure would be about 120 over 70, and that's milligrams of mercury. It's a measure of pressure. 120 over 70 is about normal. Okay, so what about the veins? Well, the blood is being driven through the arteries by the heartbeat. What about through the veins? There's no pressure in the veins. There is virtually no blood pressure in the veins. So how is blood moved? Because the blood has to be gathered up and moved from distant parts of the body back up to the heart and then to the lungs. Well, the answer lies in the structure of the veins themselves. The veins, you remember, have thin walls, but all the way along the veins, there are valves, very regularly spaced valves. And here, you can see here, these are closed. And the result of this is that blood flow in veins is in one direction only. The blood, hopefully, can't flow back. I'll give you one example where it does, but here, the blood flow is towards the heart simply because of these valves. But in order to drive the blood, we've got to actually squeeze the veins. And we do so with bimuscular action. There are really three examples of this. The first is by our voluntary muscles. Our daily movement continually compresses and relaxes our veins. And that pressure on the veins, squeezing them, drives blood in one direction because of these valves. It moves it towards the heart. The second instance is just from the action of breathing. As we breathe in and out, we exert pressure on all of the veins, especially in the thorax, and that drives the blood towards the heart. The third instance is through involuntary muscle movement, for instance, in the gut, as gut peristalsis and all of this sort of thing goes on. That also squeezes the veins continuously and drives blood through them. So flow through the veins is under very low pressure, and it's also just a passive flow towards the heart. I said I'd give you an example of when these didn't work. You must realize that because of the system, the blood pressure inside the veins especially is under a lot of influence of gravity. And if you're driving blood up towards the head the whole time and you're a bipedal animal, you've got to work against the force of gravity, which is asking this blood to pool, actually. If these veins fail, the blood does indeed begin to pool, and you begin to get the veins have no real big strength to them, to the wall. And this is the cause of varicose veins. Varicose veins are a uniquely human invention because of the fact that we walk upright, and especially in the lower part of the body. Sometimes in certain areas of the veins, these valves fail, and the vein begins to balloon out in that visible varicose vein that we recognize. Okay, so as I told you, blood pressure is something which is very carefully monitored by the body. In fact, it's monitored by the brain stem, for example, and is very, very carefully regulated. There are numerous physiological mechanisms, even involving the kidney and all the other kinds of organs that you might not realize were involved in blood pressure regulation. There's a whole set of these homeostatic mechanisms to regulate arterial blood pressure, to ensure especially that the brain receives sufficient oxygen continuously. Also to provide, when you're exercising and everything, to provide enough oxygenated blood to muscles and that sort of thing, obviously. The blood pressure is very largely regulated through regulating the diameter of arteries and arterioles. Please make a note that there is an error on your on the handout. I mean, on the PowerPoint set. Here it says by altering the diameter of arterioles. I've taken that out and put here vessels, because there are many blood vessels whose diameter can be regulated. Especially in the arteries and the arterioles, you remember there's that muscular lining, there's that muscular layer, and this is what it's there for. It's there to regulate the diameter of those vessels. And that diameter is largely regulated through the autonomic nervous system, but also there are also hormonal influences as well, which can induce those muscles to either relax completely and allow the vessel to increase in diameter, or to contract and decrease the volume. So let's think about it this way. You've got a set number of these pipes running through your body. There is a certain volume of blood which is being percolated through your body through those pipes. If I induce a whole lot of the arteries to contract, to decrease their volume, what is it going to do to the blood pressure elsewhere in the body? is going to force a greater volume of blood to have to make its way through a reduced volume of arteries. In other words, the blood pressure is going to rise. If I start contracting vessels, I'm going to cause blood pressure to rise. If I relax vessels, the blood pressure is going to fall. Coupled with that, don't forget, we can also regulate the rate at which the heart is beating, and we can regulate stroke volume. And so the body, by these simple mechanisms, can exert very, very fine control over the blood pressure. The contraction we call vasoconstriction. It's the contraction of smooth muscle in the artery and arterial walls. Vasodilation is when the diameter increases and is associated with a lowering of blood pressure. Just as a little side note, it's been discovered that one of the most important influences on diameter of blood vessels is a gas. And it is a gas which is acting as a hormone, which is a very interesting situation because it's very unusual. But the gas is nitric oxide. And it won't surprise you to learn that the very popular pill Viagra, Viagra has influences the body by causing the release of nitric oxide, especially in the genital region. That's how Viagra works. Okay, it increases the dilation of blood vessels with obvious effects. There are various other ways hormones involved. One of the most important is a hormone called endothelin. And endothelin is a strong inducer of vasoconstriction. So by varying the diameter of the blood vessels, by varying stroke volume, etc., the body is able to exert homeostatic control over blood pressure. Okay, I think I've covered that. All right, so let's just think for a minute about how the circulatory system is working. We've got the blood leaving the heart under high pressure. It's being driven under high pressure so that it can be distributed far away from the heart and quickly. So the blood actually moves very rapidly through the arteries. If we come to the other side, we look at the veins coming up to the heart, and we look at the blood there. There's very low blood pressure, and the blood velocity is very, very low. If you cut a vein, you will see it just bleeds slowly and pools. Cut an artery, and it gushes out under the impulse of the heartbeat. So this is very interesting. Let's have a look at how arteries and veins link up with one another, because this is a closed system. The blood moves from arteries to veins directly. It doesn't pool in the body and then get sucked up by the veins. It goes through vessels that join up together with one another. Here are the arteries. They divide into arterioles, and then they divide into arterial capillaries. And those capillaries join up with venous capillaries, which get to join with one another, get thicker and thicker and thicker, and eventually form the veins. So this here is called a capillary bed. And it's the most important anatomical feature just about of the entire circulatory system, because this is where the blood circulatory system communicates with tissues of the body. This is where all of the exchange takes place, the exchange of nutrients, the exchange of oxygen, and the exchange of carbon dioxide. So if we look at the area, the surface area devoted, the surface area of the arteries, of the great vessels, is in fact rather low. There are only a few of these big vessels, okay? So it's low surface area. We get to the capillary bed, the surface area is enormous. As we go away from the capillary bed, the surface area drops as we go to the, so the capillary beds, the surface of those blood vessels in the capillary beds is very, very big compared to the surface area of the greater vessels. If we look at the velocity of the blood coming through them, we follow the velocity of the blood in the arteries. We already know the velocity of blood, the speed at which it's moving is high inside the arteries. What about the veins? The veins, very, very slow. It's extremely slow because it's just being driven by passively by muscle movement. It's very slow. So we've got blood moving fast. We've got blood moving slow. What happens here? If I've got blood moving very fast through the arteries here, and I suddenly stop it, what is that like? Well, that's like me having a hose, right, with water going fast through the hose, and I kink the hose, and I stop the volume, or I just, I pinch the hose, and I reduce the diameter of the hose. What is going to happen? I'm going to cause a rise in pressure inside that vessel. There's going to be a big pressure rise. And that is exactly what happens here. As these vessels decrease in diameter to form the capillaries, the velocity of the blood is drastically slowed down. And as a result, the pressure rises. And the pressure, and in fact, as the heart beats, we get a little burst of increased pressure all the time. And yet, on the other side, there's very low pressure. There's very low pressure in the veins. Do you see the problem? We're generating this high pressure in the capillaries, but that pressure has dissipated by the time it goes to the veins. Something has to have happened. Somehow or other, we have to dissipate that pressure. Otherwise, these capillaries are just going to burst. And the way in which that pressure is dissipated is by drastically reducing the volume of the blood. We drastically reduce the volume of the blood which goes into the veins. And we do so by losing fluid. Under pressure in the capillary beds, fluid leaks out of the capillaries into the tissues around them. And when it does so, when that fluid moves into the tissues around them, it carries with it oxygen and it carries with it all of the nutrients. And it bathes the cells around it in a nutrient oxygen-rich environment. So here's the way it works. As those capillary beds form, the pressure rises tremendously. And that causes fluid to flow out under the blood pressure, flows out across the capillary walls. This is called the interstitial fluid. You'll also see it referred to as serum. And serum is a special term for blood which has had all its blood corpuscles filtered out of it. And that is what happens. Only fluid, salts, and nutrients and things like that dissolved in the fluid flow across the capillary walls. The blood corpuscles, the white and red blood corpuscles, everything else, all the blood components stay inside. They are filtered out. They can't get across the wall. There is also a flow into the capillaries, I have to tell you, and that is by osmotic pressure. The osmotic pressure continually causes a flow into the blood vessels to maintain, so that the osmotic pressure here is the same as here. But towards the arterial end, the blood pressure is so great that it forces a flow into out of the vessel and into the surrounding tissues. I will tell you right now that we do obviously get a certain amount of flow back in through osmotic pressure, but the rest of the fluid, the extra fluid that is percolating now out of the capillaries into the tissues, that is actually gathered up by a system of lymph ducts. That is their responsibility. The lymphatic circulation picks up the serum and recirculates it. And when we talk about the immune system, we'll see exactly how that is done. This is the way in which these fine capillaries, without bursting and releasing blood, this is how these fine capillaries communicate with the tissues that they go through. They communicate with this fluid that flows out through the walls to form the interstitial fluid, rich in oxygen, rich in nutrients to supply these cells. At the same time, carbon dioxide percolates into the serum and into these vessels to be transported to the heart. Okay, so I've hinted at the fact that this serum is going to be picked up by the lymphatic system. When there are various names for that fluid. It is the interstitial fluid, in other words. It is sometimes referred to as serum, and the serum is simply blood, and it's basically blood plasma. It's blood that that does not contain its blood corpuscles of any sort. But it's also, when it's associated with that lymphatic system, we refer to it as lymph. It's all the same thing. And the lymphatic system gathers up all of the lymph, restores, and has to now somehow or other restore the blood volume, because we've lost some of the blood volume by losing that fluid. And it is gathered up by the lymphatic system, and it is actually dumped back into the circulatory system right near the heart. It is dumped, the lymphatic system empties into veins called the subclavian veins. Subclavian because they're just below the clavicle here. And the lymph vessels, by the way, work in much the same way as veins do. They are passive. There's no active pumping in the lymphatic system. Instead, they are vessels with valves in them. They look much like the veins. And the lymph is percolated through them, pumped through them by muscle action. And you can see this in real time. Because if ever you've taken a very long plane flight and you've just sacking out watching the movies on the little TV screen in front of you without moving for a long time, you've taken your shoes off, have a look at your feet, because it's perceptible that when we sit for a long time without moving, our feet begin to swell and our ankles begin to swell. It can actually become quite marked and so bad that you can't put your shoes back on. And this is simply because the blood capillaries that pass through your feet are leaking as they should. They're leaking interstitial fluid into the surrounding tissues, but your lymphatic vessels are supposed to be picking it up and retransporting it into the circulatory system. But if you're sitting still and not moving, the lymphatic vessels work and the venous system works by muscle contraction. If you're not contracting your muscles, all that interstitial fluid is going to begin to build up and begin to swell the limb. It's not a problem. All you have to, in the case of a plane flight, all you've got to do is start wiggling your feet, squeezing your feet, contracting them, get up, go for a little walk, etc. And you'll see it soon dissipates as it's moved back into the circulatory system. That swelling, by the way, is referred to as edema. And if you're sitting in a plane, it's called a benign edema. It's got no consequence. But it is sometimes, edema is sometimes a sign that something has gone wrong with the circulatory system. Okay, so we'll leave it there for today. And then I'll remember that on Friday, you have your test. that the grade for this test coming up on Friday will appear as your midterm. It's not really a midterm. It's just a test like any other class test, okay?
I have a question, Professor.
Go ahead.
I have two questions, actually. One question, can you just go over the chapters that we need to know for the test on Friday? And two, is the test going to be open like all day, or is it going to be like how you normally do it from like 8 to 10?
I normally expect that it will be done during class time. The chapters we're covering, I can't, off the top of my head, I can't remember, but I've sent you an email, and I make a note now. I'll send an email to clarify again. All right.
Okay, and then I'm going to send you an email asking if I can take the test at a different time, because I have to be at work at the time during the test.
That's fine. That's okay. Just let me know. Just let me know. Yeah. I'll set a time for you. Okay. Anybody else? All right then. So then I'll see you. Well, I won't see you, but good luck on Friday and enjoy your spring break.
Thank you.
You too.